students, welcome back. So we have been looking at the inadequacy of the liquid drop model in the part A of today's class. Now as a consequence of this inadequacy of the liquid drop model came the shell model of the nucleus. So let us move on to what is the shell model and why this came about actually. And the main point was that in the liquid drop model, what we talked about is about the whole nucleus as a whole, but we did not talk much about what happens to the individual nucleons and all these things. What about the energy? It is found that nucleus is in different energy states. So why and what are the quantum numbers and all these things could why how the difference between the states came about, those things could not be explained by the liquid drop model. Now again during the time the magic numbers were also discovered, which I had mentioned in the first unit. We had seen that these are certain numbers 2, 8, 20, 28, 50, 82, 126. Now what are these numbers? These numbers are those numbers for which if n and z takes these numbers, n or z or both n and z, then they are found that these are very stable. That means very stable and their binding energies are very big. This we saw in this binding energy curve of A versus binding energy per nucleon, and we found that this graph was. So you see now students how many times we are using this graph. So this graph in the beginning when you study the binding energy curve, since it's given in the first unit, we hardly realize the importance of this. It is first of all we saw that when we look at these minutely, we find some peaks here like this. And what does these peaks correspond to? These peaks correspond to A values having magic numbers. And what are the magic numbers? They are 2, 8, 20, 28, 50, 82, 126. So these are the said to be. Why they are said to be magic numbers? Because you see the graph follows this pattern and suddenly we have, that means the energy, binding energy per nucleon should increase in this way, but we see suddenly this are like this. So this is one thing that could not be explained at the time, and this is one of the reasons for which nuclear shell model was adopted. At the time, since most of the things about the nucleus was found out as in comparison with that of the atomic world, so people thought that if in the nucleons, in the atom, we could describe each of the electrons by the motion of each of the electrons in a shell structure. We know they are in a twice n square, this kind of a thing where n is the number of the orbits. So this is 2 into 1 square, which is equal to 2, 2 into 2 square, which is equal to 8, and 2 into 3 square, 18. So we knew that these orbits required this many. The first orbit required the 2 number of electrons to complete its orbit. Then we saw that the second required 8 numbers and the third required 18 numbers. These things we learned in the atomic context. So people even thought that maybe is there some kind of things. They also found that some of them are very, very inert. They are very stable. So they are so stable, means they don't react with anything and all these things. This might be because of some kind of closure of this orbits, if there are orbits. So again, so with this idea, the nuclear shell model was adopted, and actually it was quite late in 1948 that Mayer suggested nucleus with this abundance, having this abundance in nature. It is found that those elements which have got N or Z or both N and Z as these numbers are very abundant in nature. Now, what is the meaning of being abundant in nature? Being abundant in nature means they occur naturally. And why do they? Because some elements, they immediately react with nuclear, they immediately either they decay or they may react with some other, they get decomposed to other elements, but mostly those which are found abundantly means their binding energy must be very big, and this abundance is related to the magic numbers. I don't know whether I have been able to explain it properly, but this abundance in nature is related to the magic number. So this also gave the scientists enough reason to think that yes, there is a shell structure in the nucleus. So there are several evidences about it. Just like suppose above Z is equal to 28. Suppose above Z is equal to 28, that means Z greater than 28. The only element which has got isotopic abundance is strontium with N is equal to 50, then barium with N is equal to 82, and Ce with N is equal to 82. So you see, these are all magic numbers, isn't it? This is one. Then again, it is found that tin with Z is equal to 50 has got 10 isotopes. Just imagine 10 isotopes. That means so many. So isotopic abundance also shows that binding energy is big. So like this, and there are numerous examples which I'll share with you. And it is again found that with Z is equal to 50, which is Sn, and Pb, that is lead, with Z is equal to 82. For these it is seen that the capture cross section is very much smaller than their immediate neighbors. Now I must explain what is capture cross section. Capture cross section is like this. Let me clear my board. See, when I write a nuclear reaction, suppose I want to make a reaction between X and Y, or I want to make a nuclear reaction. It's not like atomic reactions. You cannot just take two elements and make them meet like this, make them react like this. So in much of the cases, a particle is being hit on that material. This is said to be the incident particle, and we have a nuclear reaction as a result of this. But the thing here is not like hitting a big ball with a small ball. Here in nuclear reactions, there has to be a probability. There is a probability of any reaction happening. This may not even happen, even after being hit, even after the element X being hit by a certain incident particle such as proton or something. So in that case, some particles have got greater reaction cross section, some elements have got greater cross section, some reactions have got greater cross section, and cross sections means the probability of happening of the reaction taking place. So this probability is found to be very low for magic number particles. That means why? Because they are so stable they cannot be broken actually. So that is another particle. So here we are learning only about the evidences. Whatever I have mentioned now are just evidences of existence of a shell structure. So this is very important from an examination point of view. So please take this as something important. And then now when I say shell structure, that means it is very difficult to make up this shell model by comparing it directly with the atom. Because you look at the atom, in the atom we have a we have a nucleus, positively charged nucleus along with the electrons and the electrons. So what happens is that due to a force experienced by an electron in its orbit, in its shell rather, is the Coulomb attraction between them, just like in case of sun and the planets. So the planets, you see, they move about, the necessary centripetal force is being provided by this Coulomb force between them. But what about the nucleus? We don't have any central thing like this. And here see, you have a force, this force, and we know that the origin of this force is Coulomb. And we know that for every force there must be a potential, because what is potential? It is the work done in bringing a particle from infinity to that point like this, because from bringing electron nearer and all these things are there. So here we have all protons. Let this be the neutrons and these be the protons. The darkened ones are the neutrons and these are the protons. So we have full of them. We have no central thing, anything central out here. So what would be, and we cannot deny the fact there is a force, there is a very strong force acting here. The force is there. So the problem came up in the shell structure of the nucleus when people went to give a mathematical form, because without a mathematical form a model would not exist, because this mathematical form should be able to describe the characteristics and observations about the nucleus. So there is this force, and is there a very strong force, and what this force is has got so many characteristics. Some of them are opposed to each other, like it's so strong but it acts to a very small distance, then it is repulsive when it comes nearer, and it's same for all kind of particles, and these things are there. So that means this force, just to tell that it's a force is not enough. What would be the potential of this? What is the potential? So in this case, so many things were given, so many suggestions were made regarding the potential. There were different types of potentials were suggested by different people, and we have the different models, different shell models. So we'll talk about the different shell models in part B of today's class, part C of today's class. But for now we will know that yes, after much argument, much study, much observation, people has arrived at the shell model. Yes, they have agreed that shell model is there, and shell model is now the accepted model because it can describe the very fine structure of nuclear energy and all these things. So I'll stop here and we'll meet in part C.